320 for the small version. For the long version, which is 75 kilowatts hour, is 400 kilograms. Yeah, so this one I have in the next slide. So the car Toyota is heavier also than Tesla. The power to ratio, so the amount of power that it has for the weight of the car for Toyota is only 61, and the Tesla Model 3 is 120. So it's much more powerful car, the Tesla, than the Toyota. This is another table which talks about different things. So says that Toyota is more expensive than Tesla. The weight, as I showed you before, this is for the prolonged battery, the long-range battery. The 1600 is for the low-range battery. Tesla has a higher distance. It's 334 miles, 112 miles for Toyota. The fuel tank is 5 kilograms. That's this bar I already mentioned. Another interesting aspect in this table that I want to mention is that the energy to recharge from the source is much higher than the energy that you require for Tesla batteries. This is looking at, for example, wind power. So you have a wind turbine generating energy, and from this wind turbine, you need this amount of energy to fill up the battery, even though the battery only has 60 kilowatts hour of charge. But the Tesla is much smaller because it's more efficient, because for hydrogen you have to pressurize, you have to produce hydrogen, which is very inefficient. So compared with the energy required to use a hydrogen car, you need 2.3 times more energy from wind power. So you need 3.2 wind turbines to operate this hydrogen car. On the other hand, Tesla, you only need one wind turbine. And the cost to fuel, so the costs, so this is the energy, the cost is 5.4 times higher, because electricity is a commodity which is used for several different utilities. It's a cheap commodity, but hydrogen is expensive, so it's 5.4 times more expensive. Of course, this cost is supposed to reduce substantially in the future with the creation of a hydrogen-based economy. Maybe in 10, 20, 30 years, the costs of both fueling both cars will increase. But at the moment, batteries win in almost all the parameters. Of course, with new technologies of how to store hydrogen, of fuel cells, the increase of efficiency of fuel cells, you will have this and these values reduced. Regarding the markets for lithium-ion batteries, the main contributor for the increase in the last 5 years is the batteries, so lithium-ion batteries. But it's also used for ceramics, it's used in grease, air conditioning, medical purposes, polymers, metal making, and other purposes. And regarding that container that I found in Alibaba that I mentioned for a battery, I show you the calculation, but I didn't show how I calculated. Given that this is a lecture, I might as well show you how I calculated this, which is not very complicated. You basically have the cost of dollar per kilowatt hour. So the capacity that you have, the storage capacity you have in your battery, which is this, $1,200 per kilowatt hour. You just divide by 1,000 here. And the way I calculate, which is very simple, is to get this investment cost, because it's in 1 year you buy a battery, you have to put all your money in the year that you buy the battery. So you have to take into account the discount factor and the amount of years that you will use this battery. And the discount factor, in order to calculate the discount factor, it's this equation. And then the discount factor for 8% rate of return in 6 years, it's 4.6 years. And given that you will use this battery, I mean, we assume that the battery will be used 365 times. This means that in 1 year, you generated 365 kilowatts. And how to calculate the cost of this? You get 200, which is the investment cost. You divide by the discount factor, and then by the amount of energy they generate. Then you have the cost, the levelized cost for your battery. If you want to add operation costs, maintenance costs, and maybe fuel costs, because it doesn't have an efficiency, you just add these costs, but you don't subtract by this, because this is a capital cost, which is this is the discount factor, which is only works for the capital cost. So you will have, for example, if you have a operation cost of $10 per let's say $200 per year, which is very small. You just add $200 to this cost, because this is the cost for. This is just the capital cost. It only assumes the capital cost. And then you add the cost and you divide how much energy you produce in that year, how much is the operation cost of that year. So the capital cost of that year divided by the amount of energy that you generate with this battery. Is that clear? It's a very simple equation. I'll leave it here and send you the slides. Another interesting aspect is that, for example, batteries, so these lithium-ion batteries, they have in order to be used for driving, for electric vehicles, it has to have a very high performance, has to have a very high voltage, it has to perform very well. But, for example, after some years, after 6 years, 10 years of usage as electric vehicles, these batteries can be repurposed in order to be used for energy storage, for a house, for a business. So this is also another use for electrical batteries, EV batteries. So you buy a car, electric battery car, and then in the end you can't sell it, because no one's gonna use for a car, because the quality of the battery has already run down substantially, but it can still be used for electricity storage. And then after, of course, this battery cannot even be used for electricity storage after more 10 years. You can recycle the battery in order to not to waste the materials which have a lot of value inside the battery. So this was just a recap of last week's lecture and the things that I didn't really have time to finish. Does anyone has a question about the lithium-ion batteries? Okay, so let's start with redox flow batteries. So redox flow batteries has a different configuration. They have a anolyte tank and a catholyte tank, and it's in a liquid form. So these components, these chemical components, has to be pumped into this fuel cell. So you have fuel cell here. You have an electrolyte, you have the cathode, you have the anode, and then you have a fuel cell here, which the whole system is called a battery, but you have a fuel cell here in the between to exchange ions between these components. There are several types of redox flow batteries: hydrogen, lithium, bromide, iron, tin, iron, titanium, iron, chromium, organic materials, vanadium. So today we're going to talk more in details about the vanadium and the organic, which are the ones that are receiving the most focus. And so this type of solution, this type of battery is very interesting because it's scalable. The problem with lithium-ion batteries is, for example, a Tesla car has 7,000 small batteries, and they're not scalable. If you wanna make a battery that fits a specific need, you have to have a whole new factory. It's very complicated. It's very complex. The process for building these batteries is very difficult to scale. So, for example, if you want to store energy for a house, you might need, for example, 5,000 small Tesla batteries. However, with this system, redox flow batteries, you can increase the size of your tanks according to the amount of energy you need to store. So you have that characteristics that batteries has: energy storage and power delivery. And the energy storage are these tanks. So you just increase the amount of chemicals, of components in your tanks. And in order to increase the amount of power that you can produce in your redox flow batteries, you have to increase the amount of these fuel cells, these membranes that exchange the ions between one side of the other, is the cathode and the anode. This is the vanadium redox battery. I'm gonna talk a little bit more. So vanadium is here. It's close to niobium. Brazil is the country with the biggest reserves of niobium. We're gonna talk about the components, the resources in the future, but this is a very good strategic capacity. And I'm going to explain this vanadium with the picture below, but then we're gonna watch a video which shows like exactly with graphics how it works. I think we might as well just watch the video now. I'm gonna give you the link in the chat box so that we can all watch the video at the same time. Is that okay? Because if I explain, it's much better to watch a video because it has all the graphics and all the. So can everyone open the.
Yeah, it's good. It's okay.
The Schmid vanadium redox flow battery consists of two tanks storing vanadium analyte and cathodite. Pumps are used to flow these electrolytes through adjacent half cells separated by an ion exchange membrane. Within the half cells, the electrolytes are chemically oxidized and reduced to reversibly convert electrical to chemical energy. An external electrical power source like PV installation supplies the energy to charge the vanadium redox flow battery. The two vanadium electrolytes are flown through the cell stack in which the electrical energy is converted to chemical energy. The electrolytes charged within the cell are flown back to the tanks, increasing the battery's state of charge. Looking into the cell at the molecular level, vanadium-3 and vanadium-4 enter the electrochemical cell. At the catholyte half cell, the vanadium-4 is oxidized to vanadium-5. This chemical reaction yields an electron which is drawn off by the conductive electrode material and a hydronium ion which diffuses across the membrane to the opposite half cell. At the anode half cell, the electron which has traversed the external circuit reduces vanadium-3 to vanadium-2. The hydronium ion which has passed the membrane balances the overall charge of the half cell. The two electrolytes leave the half cells in a charged state as vanadium-2 and vanadium-5. Once the grid cannot provide energy to the battery system, the vanadium redox flow battery swaps to discharge. Vanadium-5 and vanadium-2 ions carry the chemical energy into the cell stack. The chemical energy stored within the two electrolytes is converted to electrical energy, feeding the external load. At the molecular level, the reverse of the charging reaction occurs. Vanadium-2 is oxidized to form vanadium-3, releasing an electron which carries the electrical energy. For charge balancing, a hydronium ion crosses the ion conductive membrane. Vanadium-5 is reduced by an electron under consumption of a hydronium ion. The electrolytes leave the cell in their discharge states in the form of vanadium-3 and 4. The vanadium redox flow battery delivers electrical power until the electrolytes within the two tanks are completely discharged. The Schmid vanadium redox flow battery can be independently scaled for appropriate power and energy. Power can be adjusted through cell size and number. Energy is defined by the tank volume to perfectly meet the customer's needs. As the electrochemical reaction takes place in the electrolyte solution, no loss in power or capacity takes place due to side reactions as observed in conventional batteries. This fact ensures lifetimes superior to any other electrochemical storage. Even deep discharge does not influence battery health. Unlike other flow battery types, the all-vanadium redox flow battery incorporates vanadium in both electrolytes, eliminating battery deterioration through cross-contamination. The composition of the electrolytes, vanadium salts solved in dilute sulfuric acid, guarantees low hazard potential and best possible ecologic properties. With all these benefits in cooperation with low production costs, the Schmid VRFB is the appropriate means for renewable energy storage.
It finished for me.
So did you guys understand? Let me just recap. So when the battery is charged, you have vanadium 5 plus charges. Right, so when the ions are 5 plus and 2 plus, they are completely charged. So if you have this tank full of vanadium ions 5 plus, what happens is that, and the other tank, vanadium 2 plus, the battery is charged. And you can have all the molecule or all the vanadium molecules, 100% of them, plus 5 here, and all vanadium molecules plus 2 in this side. And the opposite is you discharge, you turn from this side vanadium to vanadium 4 plus, and then also the other side vanadium 3 plus. So you reduce the distance between the oxidation levels. 5, 2, again, 5, 2, and then 4, 3. The closer they are, the less charge you have. The further apart they are, the more charge you have. The benefit of having the same molecule with such large oxidation potential is that, for example, if you have a leakage between vanadium from one side to the other, the only thing that's going to happen is they're going to lose charge. And for example, the vanadium 2 will become vanadium 4 plus, and you lose charge. But if you fix the problem, if you for example, your battery is not generating as much as it was in the past, you just need to change this fuel cell to change the whole pack, the whole battery. And this makes this type of technology to have something like 20 years of life cycle. And it can be operated regularly, and there are a lot of benefits. One funny fact is that vanadium 5 is yellow, vanadium blue is, vanadium 4 is blue, vanadium 3 is green, and vanadium 2 is purple. For example, if you want to know if your system is charged, you just look at the color of both tanks, and then you can know if the battery is charged or not, which is an interesting fact. Yeah, the video already mentioned. So basically, one thing that he doesn't mention is that the energy density is around 10 times smaller than lithium-ion batteries. So, for example, this solution is not a good solution for transportation. It's a good solution for grid storage, so storing energy at night to generate during peak hours. Japan has an example of these vanadium fuel cells, 60 megawatts. These are the fuel cells. They operate at higher temperatures, so they use the solar thermal heating capacity in order to increase the efficiency of the fuel cells. These are the tanks with vanadium ions. China is building, is about to finish 800 megawatts plant for these vanadium cells. These are the tanks that store vanadium. Oh, sorry, these are not the other tanks. These are the fuel cells in order to change the ions. These fuel cells, they are similar to, for example, a hydrogen car fuel cell. They have several layers connected to each other. It's not one membrane. There's several small membranes connected to each other, and then this hydrogen, the protons, they pass through the membrane to generate the charge. Compared with lithium-ion batteries, they have a peak performance. In the beginning, they have small performance, they peak their performance, and then they decline in 6 years or 10 years, depending how much you use the lithium-ion batteries. However, these vanadium flow batteries, the capacity, it's maintained. It doesn't deteriorate. So, for example, if you want to apply lithium for your storage solution, if you use only for 3 hours your battery, lithium would be cheaper. But if your energy storage is for 5 to 10 hours, vanadium becomes a better solution. So lithium-ion batteries is more for large power delivery, and vanadium batteries are looking into more energy storage solution, long-term energy storage solution. I also found these vanadium energy storage batteries in Alibaba, so you can buy in China. If you have $6,000, for example, you can buy a 30 kilowatt hour redox, vanadium redox flow battery, which will cost you $533 megawatt hour. So applying the same calculation in order to compare with lithium-ion batteries, we have the cost is higher because lithium-ion batteries are $200 per kilowatt hour. Of course, there's a lot of people investing in lithium-ion batteries, not so many in redox flow batteries, vanadium redox flow batteries. So if companies start to put a lot of money in vanadium redox flow batteries, this cost will reduce substantially. Assuming the same rate of return, however, 20 years of operation, as I mentioned, the discount factor increases to 9.8 years. You also you'll charge the battery 365 times per year. So in one day, you charge and discharge every day. So then the levelized cost is 533 divided by discount factor, divided by the amount of energy that you produce. And then the cost is $148. Which results in 818 reals per megawatt hour. So $150 is 818. I put the number here to compare with lithium-ion battery, but it's wrong. You get the right one. This is the right one. But with lithium-ion batteries, even though it only operates for 6 years, given that the rate of return is 8% per year, the cost is 651. Sorry about this, I forgot to put the 6 here, so 651. It'll make more sense to invest in lithium-ion batteries today to provide electricity storage for a grid, for a house, for a shopping center. However, these costs are supposed to reduce if people invest and improve this technology. So who in the world has vanadium resources? The main country with the most reserves is China. Then it's Russia. So China has around 50%, Russia 25%, Australia has 2.1 million tons, 17%. Oh, sorry. So the third one is South Africa with 3.5 million, 17%, then Australia, and then Brazil. Brazil has a small amount, is the fifth one with the most reserves. So, for example, Brazil could start investing in vanadium technology because it has resources. This, even though it's a small amount, can produce a lot of batteries. So vanadium usually is used as a steel alloy to increase the strength of metal, and is also used for aerospace metals, chemical catalysts, and now started being used for batteries. The main country that consumes vanadium is China. So China is putting a lot of vanadium in their steel to improve the quality. Vanadium consumption is increasing rapidly. In the last 20 years, it's more than doubled the production and consumption. And it's one company which produces these batteries suggests that in 2025, 30% of the grid energy storage with batteries will be provided with redox flow batteries. But of course, he's very biased. Like he's a guy that wants to sell batteries. So his proposal is not 100% reliable, but we can think that this could be a possibility. The production of vanadium is made in China. You have Russia, South Africa, North America. Brazil has 7% of the production of vanadium. The costs have peaked with different regulations that China imposes to add to their steel. You have disruption of electricity supply, so the prices varies, but it's not so high. Has some spikes because of mainly China consuming. This is South Africa. And one thing that I found that is interesting for Brazil is that niobium is a very good component to be used in the cathode of these vanadium redox flow batteries. So if you have a lot of demand for vanadium flow batteries, probably the demand for niobium will increase. The niobium is used in the fuel cell, in the cathode of the fuel cell. So in order to increase the capacity, the power of these batteries, they will need more niobium, and Brazil could make money with this because it's the country that has the most reserves of niobium, and the rest of the world has hardly any mines of niobium. And a university in Sweden has recently proposed organic redox flow batteries, so that there are several organic redox flow batteries, but they are usually very acidic, and they're acidic in order to increase the exchange of ions, because it's easier in acid-base solutions. But so these researchers, they found that quinones, which are the fluids in both sides, quinones, they have a very good compatibility with pedots, cathodes and anodes. So the idea is to use this pedot, which is an organic compound, in the anodes and the cathodes, which facilitates the exchange of ions and generates electricity in the fuel cell. And this is convenient. So they found this researching plants. So they found that trees uses these quinones and the pedots in order to exchange ions inside the wood itself, the plants. So they use this natural experience, natural expertise in order to improve these batteries. So this is a huge breakthrough, because if you just need carbon in order to produce these batteries will become very cheap if somebody puts a lot of money, and we won't be restricted to the amount of organic of vanadium that we have to extract from China, for example. And so most countries will be more likely to invest in this technology. Countries that don't have vanadium, for example. The main purpose of this battery, redox flow batteries, is to store electricity during daily cycles for the grid. For example, during the day, you have a lot of solar power generation in your house, in your building, in your hotel, and then you don't have enough demand for this electricity, so you generate more electricity than you actually consume. So the idea of these batteries is that you store the electricity during the day, so that there's extra solar energy that you generated, and during the night, you use the electricity that you stored with these vanadium redox flow batteries or organic water-based organic redox flow batteries to generate electricity during the night. So this is one possible application, which probably is the one that will make more sense, because you wouldn't want to store energy seasonally with these batteries, because then you would need too much compounds, which will make it more expensive. So this is probably limited to daily or weekly energy storage cycles. Any questions about redox flow batteries? I'm gonna go to another topic. No questions? Everyone understood? Perfect. And not very complicated to understand. So lithium air batteries are on the other spectrum of power and energy. So the idea of lithium air batteries is to provide a lot of power with very, very, very low energy density. Lithium air batteries, as I showed you in the last lecture, can be compared with gasoline if it's fully charged. So it's as if you have gasoline in your tank, and this reduces the weight of the cars, for example, and this would allow the cars to have a larger travel for larger distances. For example, 500 miles, 1,000 miles, as it's requested. Also, lithium-ion batteries, there are several different types. Aluminum air batteries are very good for volume. So they have very small volume to power ratio, to energy storage ratio. However, that's not what we're interested on. Lithium-ion batteries are the one that has the most energy storage per weight, very high energy storage per weight. You have other molecules, which is also interesting, but of course you would want lithium air because it's the lightest components for a metal air battery. So in the metal air battery, you have in the anode, the lithium, you have the electrolyte, and then you have the cathode, which absorb air and then reacts. The lithium has to cross the electrolyte, similar to a lithium-ion battery, and stored in the cathode with the oxygen molecules. So this air cathode has space in order for air to pass through. There are different. It has to have a high area to volume ratio in order for the oxygen to be absorbed by the cathode, and then for the lithium to cross the electrode and produce electricity. As I mentioned previously, this is a prototype, is an example of lithium air battery. This is the cathode where the lithium passes through and is absorbed by the cathode, and then it's stored. So the oxygen is stored as lithium LiO, lithium oxide. So as you drive your lithium oxygen battery, what happens is that these lithium oxides build up in the cathode, and then the weight of the battery increases. And for example, in the end, you have that 33% of the cathode of the battery itself becomes lithium, and 70% is lithium oxide. Of course, in the beginning is only lithium, and then the oxygen is added to the battery, which adds to the weight and makes it heavier. So this battery is a new technology. It's not commercially developed yet. It's starting in research area. And the most difficult part is to recharge the battery. So to remove this lithium oxide just by adding charge. So if you charge the battery, you're supposed to turn all this lithium oxide back into lithium, and this step is very complicated. And it hasn't been 100% proved yet. So there are technologies, so some technologies manage to charge the battery fully, but it's very difficult to have full charges with this type of technology. Another battery which I mentioned previously is a hydrogen battery, which is literally you have one tank with hydrogen, one tank with oxygen, and then you unite both, you produce water, and then you do the opposite, the reverse process with a reversible fuel cell, and then you use hydrogen as your chemical components for energy storage. This particular container, right, the Toshiba H21, it's interesting because, for example, it can store energy for the grid. It can produce hydrogen if you want to, for example, fuel your car. Of course, in this case, you need to take from, for example, a house. You need to supply with more water. If you just want to store energy for your house, as a battery. You don't need to recharge the amount of water into this battery, this solution. So it's kind of a two-in-one solution. It's also can be used for you to produce hydrogen for your customers, or it can be used as a battery solution. If somebody, yes. Augusto?
Hello, Julian.
Hi. So yeah, I have gone through some of the main batteries which I thought that would be relevant to go through. The most interesting regarding research, regarding application, and now I'm going to start talking about the minerals of who owns these components. For example, graphite, nickel, aluminum. So aluminum is in the US. In the UK is aluminium. I'm going to stick with aluminium. Copper, lithium, cobalt, manganese. So before I start this, it's a bit just memorizing. It's not very clever information. Some of it is clever information, is interesting information. But do you guys have any questions so far about these technologies, this battery, how they work? Okay, so let's keep going. This is the expected increase in metals for lithium-ion batteries in the future. We're on cobalt, so not only cobalt because you have manganese here, so several different batteries. So this is until 2030, the demand for these metals will increase exponentially. We are here, so it would increase in 10 years, something like 10 times, maybe 15 times. That's the expected increase demand for batteries. And I'm going to start with graphite. Graphite is what we used to write when we kids, when we used to go to school. We have these graphite, it's used in your pencils. And these graphite are minerals which produces these structures. They have these structures which are a combination of graphene. So it's a natural form of graphene which is used in lithium batteries to store the lithium. And I can increase the screen because the size is too small. So in the world now we have that Brazil produces 10% of graphite, China 75%, and others 15%. This graph is from 2017, so might have some changes up to today because of the increase in demand. So for example, if you want to rush for gold, go work for a company that mines graphene, process the graphene in Brazil, and then, or you can create your own company. Brazil has a lot of graphene and make a lot of money out of it because everyone wants to buy graphite. Sorry. This is a map showing the whole life cycle. Right? So Brazil produces a large amount. China produces also large amounts. And then you have all the other steps for the production of the graphite required for use in these batteries. It's a very complex process. So they focus mainly on the participation of Canada in this slide. China produces in the most amount. So in this graph, India already took over. So India is in the second place. So it's difficult to find data on these resources, like how much country has how much mine resources. So I could find, but some of the data they are not agreeing with each other. Of course, some people want to say that I have more, you have less, and stuff like this also. So some of the data is biased. So this one is saying that China has 780,000 million tons of graphite. India 150, Brazil 95, then Canada 30. In Brazil, the mines are in the north of Minas Gerais. There is one in the south of Minas Gerais also, the blue dot here. And there is another one here close to the Furnas Dam. Yeah, so we have graphite. Nickel. So nickel is also very important. Nickel usually nowadays is used for stainless steel production. It's also used in batteries. 5% of the production of nickel goes to batteries. The nickel reserves around the world are mainly in Australia. They have a small island in the Pacific called New Caledonia, which is probably all made of nickel, because it's a very small island, has 15% of the resources of nickel. Then Brazil. So Brazil also has a lot of nickel. So also interesting potential for Brazil. And the nickel production, the main countries, Russia, Indonesia, Philippines, Canada, and Brazil is only produces 5% of the nickel around the world. And the cost of nickel is expected, the annual supply. So the supply of nickel is expected to increase double in the next decade, because of the increase of batteries. Batteries, last lecture I showed you that the main component of Tesla ion batteries is nickel. You know, if you remember, so it's nickel, cobalt, and then lithium. So the most important is nickel. So it's very important to have very cheap nickel in order to lower the price of batteries. And I found that Vale is expected to be producing the most amount of nickel for the world consumption. So by the end of 2020, Vale will be the biggest production of nickel. This data is from 2011, so it's very old. Vale invested a lot of money, and now in the end of 2020 will be the biggest producer of nickel. One of those information I, for example, didn't know 2 days ago, and I think is interesting and important to share with you for this new world order, new battery world order. Vale is going to be producing. Another one is aluminum. So Brazil also produces 12% of aluminum, 15% produces in Guyana. Guyana is in South America, it's close to Brazil. China produces 22%, Australia 28%, and the others produce 21%. The world reserves are mainly in Guyana, Australia, Vietnam, Brazil, Jamaica, Indonesia, and other countries as of 2018. Of course, these data, they vary substantially, so it's important to really want to work with this, write a paper to look at several different sources. So the production of aluminum first. So this is aluminum. I said nickel, sorry. Aluminum is the minerals called bauxite. Bauxite. I don't know how to say in English, bauxite, or never said that in English. The production, this graph is different to the other one also. So Australia in here is producing 25. China is similar, but in that one, Brazil was producing 15%, and this one is producing 9%. For users of aluminium is in automotive industry, construction, consumer goods, foil and packaging, as we use while cooking, we use aluminum to to conserve the foods, electronics, machinery, and of course, these electronics will increase with the use in batteries. Copper. Copper is also important. So copper is produced in Chile, mainly. Chile is the country with the most copper reserves. US produces 11%, Peru 10%. So these are the main producers. So the Andes region and the Rocky Mountains. So these mountains here in South America, Central America, North America has a lot of copper, which can be made. And copper production, Chile skyrocketed in copper production in 1995. Now is the world leader for copper production. That was up to 2010. I'm not sure how it developed since today. They use this for construction, electrical and electronics, transportation, consumer products, and machinery. So transmission lines, they're usually made out of copper, which requires a lot of copper. It's a big demand also in the construction industry. And copper is also used for renewable energy solutions, mainly solar PV and wind. This is a future scenario that predicts that in 2050, this is going to be the share of demand for copper. And batteries is here, energy storage, but it's only 3.8% of the demand. So it's a small demand compared to the other demands for copper. Manganese, it's in Gabon, South Africa, China, Australia, and other countries. So that is a very distributed production, and you have 30% here in others. The manganese in China, for example, has very low concentration, so it's more expensive, even though it is the country that produces the most manganese. You have several other countries who also produce manganese, but they have higher ore grades, which lowers the costs. Manganese production. So South Africa, China, Australia, other countries, Brazil, Gabon. Brazil is producing a lot of these minerals. There is a mine in Rondônia for manganese, and Maxtec is the one that's extracting these manganese. Manganese cost has not varied so much with batteries, like, for example, lithium and cobalt, which has skyrocketed. The main reason that manganese didn't vary so much is that you have a lot of different suppliers. So the supply of manganese is very diverse, which doesn't make a country, for example, vulnerable or not having access to the resource. China has access, US has access, everyone's happy. The cost doesn't rise so much. For manganese batteries, there are several manganese-based batteries also, which are in the market. Manganese, lithium manganese oxide, lithium nickel manganese cobalt oxide, and the main one for car batteries are these lithium cobalt oxide. Of course, there are for different applications. I'm not sure, I'm 100% sure exactly which applications these lithium-ion batteries are used at, but some of them demand manganese. Cobalt is 61% of the production of cobalt is from the Dominican Republic of the Congo, and 39% is around the world. You see here you have the cobalt reserves, mainly in Congo. The economic viable reserves are also in Congo. Economically viable reserves you have in Australia, also in second place, and other. So probably Congo has a lot of very low grade cobalt, which might be 1-2%, which doesn't make economical sense to extract the cobalt from the ground. Here is the Democratic Republic of Congo. So putting into perspective why cobalt is such a scarce metal and what's the big issue behind cobalt lithium-ion batteries, is that, for example, these are the copper resources. So this is the content, so the total amount of metal. This is in a logarithmic scale. For example, you have a lot of copper. You have nickel, a lot of nickel also. You have other metals which are important for batteries, but then cobalt, you only have these small dots, which are mines around the world, mainly in the Dominican Republic of Congo, and it's just not so much compared. This graph is very interesting to see, just it's a very rare metal. However, we have that there is a lot of cobalt on the deep sea in seafloor nodules or seafloor crusts. I'm going to talk about more details in the next slides. And on the Earth, you have different types of cobalt, which you can find on the land. And this is the Earth deposits. And I'm not going to go into details on these Earth deposits, how they are in the crust, because if it was Brazil, I'll go more in detail, but it's only in Congo, so not so important. World cobalt production, global mine produced cobalt, so 60% in Congo, and then you have Cuba, Madagascar, New Caledonia, several other countries. Apparently Brazil doesn't, in the other countries that produce cobalt. So this is the mines, for example, in Canada. They have very small amount of tons of cobalt. They have 1% cobalt grade. It's supposed to be high, apparently, 1% of cobalt. And then you have all these in Congo. This is also logarithmic scale. So Congo has huge reserves. Not huge reserves because it's a rare metal, but it has much more than other. This is magnetic nickel group. Has much more than cobalt. Here are the price spikes for cobalt for different reasons. Every in these years they have spikes for different reasons. Lately, so in 2017, you had concerns over cobalt supply, soaring demand in batteries for transport, and the price increased more than half. Cobalt in the last 2 years, 3 years. Another interesting aspect is regarding who each country sells the minerals. And in the case of cobalt, you have that here, Dominican Republic of the Congo, and here this country, Angola. So these countries export mainly to China. It's not only to China, but exports mainly to China. And this could be, for example, a problem for supply of lithium-ion batteries with cobalt to the world, because, for example, if there is world conflicts between the United States and China, then the main reserves for cobalt will be in China's hands. For example, Brazil, Russia, Indonesia, Australia exports to both countries, so China and the US, you have that these countries in Latin America, Chile, Australia, exports both Bolivia, Peru to the United States. And it's interesting to have this in mind, just in case you have, for example, conflicts between the two countries, and then which resources will come from each country. And the dark countries export to both countries. For example, South Africa exports to both countries. Most of the world is more red to dark because China is demanding most, has the most imports around the world. It's the world factory, but US also produces most of the products and still has a huge impact on the global commerce of commodities and minerals. So going back to cobalt, the main demand for cobalt is now on batteries already. You have alloys producing metals. You have metals also, carbides, magnets, alloys, steel, and others. Of course, this chunk is supposed to increase substantially in the coming years. And this is the other solution that I mentioned, which is extract cobalt from deep sea. So deep sea mining has already been an alternative since 1970s. The US has already been extracting minerals from the deep sea. And there is not so much information about this. There are several companies that you can see. For example, Nauru. Nauru is a company, is a country that is an island in the Pacific, and supposedly it has a lot of production of deep sea mining. But of course, the amount of production is not revealed, because if not, they'll have to pay taxes to somebody. So no one knows how much is being produced now by deep sea mining. I couldn't find any data, but there are equipment, there are people working on this field, and there is a substantial amount of cobalt already being extracted with deep sea mining, but it's not revealed. It's not a data that, for example, you know. For example, the amount of wood that is sold from the Amazon. No one knows how much wood is deforested in the Amazon sold, because people don't want to pay taxes to Brazilian people for the wood that they extract. If they know that the wood is coming from the Amazon, we would be able to charge them and ask them for money to pay. And the people that are buying and selling these resources, they don't want to pay taxes. And of course, if it's in the deep sea mining, you would never want to pay taxes, because it's deep in the bottom of the sea, and no one should know about it, what you're doing in the bottom of the sea. So there are three main approaches. You have cobalt crust, you have seafloor massive sulfides, and you have the polymetric nodes. The cobalt crust are these locations, so mountains, for example, continental crusts, which have a depth of between 800 and 2,500 meters deep, which cobalt precipitates within this depth, and in the rocks that forms the continental shelves or these small islands in the bottom of the sea. And it's more sophisticated, more complicated, because you have to drill the rocks. So there are not so much investment in this type of extraction yet, because it's more complex. These seafloor massive sulfides are, for example, exhausted volcanoes, underwater volcanoes. Of course, is exhausted, because if it's a volcano, you wouldn't want to put infrastructure there, because you could be destroyed with the eruption of the volcano. So volcanoes, they are not emitting lava anymore. It's left. They are sleeping. They have high concentrations of sulfides. In the crust, we have several mines of these sulfide mines. They have rich minerals, they have rare earth minerals. But given that you have to dig through these sulfides are very acid materials, that if you mine in such mines in the land, you create huge environmental impacts. You increase the acidity of the rivers. There are mines like this, but of course they have to go through very expensive processes in order to reduce the environmental impact. But on the bottom of the sea, at 6,000 meters below the sea, people are not so worried about it. So there are some extraction of rare earth minerals from these sulfide deposits. And the other more interesting one, which there are a lot of material on the internet if you want to look through, is these polymetric nodules, which are literally it's like small potatoes, which are precipitations of heavy metals on the bottom of the ocean. And I'm going to go through more details in the next slides. So on the ocean, you have offshore in places, in shallow places, you have diamonds, gold, tin, heavy metals. Further on the continental crust, you have phosphites. On the middle of the continental crust, you have cobalt-rich crust, as I mentioned to you. You have also manganese and nickel in this region, which is great for batteries. On the edge of the shelves, you have sulfite deposits, which is rich in copper, gold, zinc, and in these polymeric nodules on the plain, on the bottom of the ocean, you have manganese, nickel, copper, cobalt, and I have no idea what's REE. I'll have a look in the next lecture. So this is what it looks like, the bottom of the ocean, where these polymetric nodes are. They are literally these potatoes, small potatoes made of nickel, manganese, and cobalt. And there are these equipment which already exists and are currently operational. They exist, they are used. And what they do is they are similar to a vacuum cleaner, which collects these stones, these polymetric nodes, and pump the polymetric nodes to a ship on the top of the ocean where the minerals are processed and sold. So of course, the advantages of this technology is that, for example, you don't need to use slavery, child labor, slavery labor. You don't need to pay a country that it has dictatorship. You don't have risks such as earthquakes, floods, tornadoes that will impact your production. You don't have, for example, wars, coups, people wanting to fight for the resources with guns, killing the mine workers and the mine managers. So there's a huge potential for these resources on the bottom of the ocean. I'm going to go through the potential, which can be explored in different countries, and no need for a huge war for these resources. It will be very good in the future. Hopefully, it will make us live longer. So manganese. So this graph compares the cobalt crust, which is the one at 800 to 2,000 meters deep, and the polymetric nodules, the potatoes. So the blue is the potato, the other one is the crust. In the polymetric nodes, you have a lot of manganese, some iron. You have 5% of cobalt, which is a huge amount. You have 25%. Oh, sorry. Here is the axis. So here, so it has 5% of iron, 25% of manganese, 0.2% of cobalt, 1.2% of nickel, 0.1% of rare earth elements. So REE is rare earth elements. You have lead, you have a lot of copper, 1% of copper, and zinc. On the cobalt crust, you have manganese, iron, cobalt, much more cobalt. You have nickel, rare earth elements, more rare earth elements, lead, and copper. So these are the earth potential, the potential for these sea mining. Yeah, Brazil, for example, has a huge amount of polymeric nodes on here and here. Maybe, for example, the leakage of petrol that affected here the northeast could have been a result of extraction of these polymeric nodes. This is, of course, conspiração, né? Teoria da conspiração, but there could be people already extracting these nodes from Brazil. You have cobalt crust in here, close to the Rio Grande do Sul, and on the coast of Rio Grande do Sul, where you used to have volcanoes. You have these sulfide deposits, which are where you can have a lot of rare earth minerals, and a lot of potential around the world. So this is a Clarion Clip zone. I have no idea what this means. Sorry. So any questions about deep sea mining? I'm gonna start talking about lithium reserves. Oh, deep sea mining is also one technology in the future, in the early future, probably today, that will become will provide most of these minerals, batteries, and will become common industry in the future. People will extract these minerals from the deep sea. You just need the technology and a lot of investments to make it viable, and then we can extract all these minerals. Of course, so this potential, of course, it's not sustainable. So if you remove this, you will remove the concentration of these minerals of the ocean. And for example, after you extract all these polymetric nodes, the concentration of these metals on the ocean will reduce, and these polymetric nodes will stop precipitating because they are formed in 10 to 100 million years. They increase in size because of the precipitation of heavy metals on the bottom of the ocean. This is around 6,000 meters deep. So lithium reserves, they have conventional brine, which is, there is a lot of potential in South America, Chile, Bolivia. I'll go through the details. It's literally produced with extraction of sand and pumping water in order to precipitate the lithium on the top, and then the lithium is extracted, consumes a lot of water due to evaporation. You have volcanic turf, you have lepidolite, you have several different rocks and clays that contains lithium, which is also another type of formation of lithium, for example, in Germany, in very old volcanic formations, they also have lithium reserves. Germany, the UK, they are investing in lithium mines that formed with volcanic, very old volcanic operation. I don't know how to say it. Volcanic activity, sorry. Other are formed with these salt lakes, that there are a lot in the Andes. So the rain dissolves the salt on the mountains. What happens is that the water doesn't have anywhere to go, and then it evaporates, and then the salt dissolved from the mountain is accumulated in a huge salt basin, and then this salt basin has substantial concentrations of lithium. Then you produce these Salars evaporation, which then you extract the lithium from. This is another representation. Right, so for the production of lithium, you have Chile, Argentina, well, Australia is the highest today. And you have Chile, Argentina, China, Canada, Brazil produces lithium also. And this is expected to increase substantially, mainly in Australia. So in 5 years, the production of lithium is expected more than double in order to supply the rising demand of batteries. This orange line is the brine, which is mainly produced in South America. This one is the produced in Australia. So Australia production will increase. It's a mineral, which inside the mineral has some lithium, which is then extracted. Lithium is also found on the ocean, as you would expect. So the reserves on the ocean for lithium is much higher than the reserves on the land, which is similar to cobalt, but cobalt is precipitation, is the metals are on the deep sea. This lithium on the ocean is not on the top, on the bottom of the sea, it's on the water itself. So there are researchers developing technologies and proposals in order to extract the lithium from the sea. And I didn't go through in detail to understand how this process works, but it's interesting, probably not a viable alternative, much better to extract from mines, but maybe if people invest a lot of money on this, it could eventually be a viable alternative. So another graph showing the potential for lithium. You have China has the highest, Bolivia has the highest reserves of lithium. You have Chile, Brazil has some, China has a combination of brine and minerals. Australia has mostly minerals. The US has in the Salt Lake City, that's Nevada, I think, the state of the US, which has a lot of salt lakes, also has. Canada has minerals. I'm gonna go through the Brazilian minerals, type of minerals. So this is another graph, just to show you a different perspective. This shows a little bit more smaller countries that has also lithium. So lithium is not a huge problem because there are a lot of suppliers. For example, if people have strikes in Chile, the problem with cobalt is only Congo has cobalt, which makes it very complicated to very risky investments to only have one supplier to provide you with the energy. So the production of lithium is divided by Chile and Argentina, Chile and Australia. Argentina has some production, China, Zimbabwe, Brazil is not here. This is the production of lithium in Brazil has kept constant. It hasn't really risen since the increase in production of batteries. Could be a potential good idea to increase lithium because the price will increase surely in the future. This is the price of lithium. Here I don't have the x-axis, the y-axis, because I'll have to pay the site to get the data, but I'll show you the next figure, the y-axis, but it doesn't go as far as July 2020. So the price in 2015 increased substantially, but then started to reduce after 2018, and now went back to what was in 2015. So the cost is 2,000 euros per ton of lithium, quite expensive. Of course, lithium is very light, so you can do a lot with 2,000 tons. And you can see 2015, it reduced back to 2010 and 2020. Here I have my axis. So the uses for lithium, I already talked about this, I guess, in the beginning. So ceramics and batteries and others, which I already mentioned. How much lithium goes to everyday item? You have Tesla Model S, 51 kilograms. So it's the size of a slim person. It's the amount of lithium that weigh in a car. Other electric cars varies from 10 to 63. Powerwalls, 10 kilograms of lithium. Hybrid electric cars, 0.8 to 2 kilograms. Tools vary from 50 to 60 grams. Laptops, 30 to 40 grams. Tablets, 20 to 30. Smartphones, 2 to 3 kilograms. The consumption of lithium has increased substantially from 2002 to 2020. From 7,000 to increased something like 3 times in 20 years. And the main reason for this rise is the increase of lithium-ion batteries. You have also some increase in alloys for metal production, glasses, ceramics, alloys, probably ceramics also, sorry. Ceramic alloys, lithium-ion battery megas. So there are a lot of big mega factories producing lithium-ion batteries. The current production in 2015 was something around 25 kilowatt hour a year of production. LG is investing, Tesla, Foxconn, BYD, Boston Fuels, also investing, most of them in China. Tesla is in Nevada. Nevada has lithium-ion mines close to Salt Lake City. Consumption of lithium is increasing substantially, will increase substantially to 2030. The cost of lithium-ion batteries is reducing rapidly, as I have mentioned already. Now I'm going to talk about the potential for lithium in South America. So Bolivia, Chile, and Argentina has the highest potential. This is the main process for producing lithium oxide minerals from Latin America. Is pumping water from the ground and evaporating on the top and extracting the lithium that builds up on the top of the surface, and then of course further processing in order to increase the concentrations of lithium oxide. So the Salar de Atacama in Chile has a small concentration of lithium, but it's higher than the Bolivia and the Argentine salars, 1,570 parts per million. And then this is the picture in Google Earth. If you want to know exactly where it is, it's in here, in this region, southern Chile. The Salar of Uyuni, Bolivia, has a huge potential. You can see from satellite images, this salar here. I'm not sure if anyone in here went to Bolivia to the salar. It's also a touristic point you can go to visit. So who is interested in Bolivia lithium? There's a lot of interest from the US, China, Germany, Japan, Russia. There's several people trying to create agreements and deals in order to extract, in order to contain these sources, because of course it's going to be very valuable in the future because of the rise in batteries. Brazil also has, I mean, Brazil should be interested. It doesn't show interest now, but it should show interest because Brazil has a lot of possibilities to bargain. For example, bargain ships, make a good contract with Bolivia, because Bolivia is a country which is landlocked. If you see here, Bolivia doesn't have access to the ocean. And Bolivia has, for example, the plantation that they have around Santa Cruz de la Sierra. They extract, for example, soybeans, but then they have to transport the soybeans up from the Andes mountains, and then pay some tariffs for Chile in order to export the product. And it's very complicated. It requires a lot of fuel. The trucks, they break down the streets. The infrastructure, the road infrastructure is not great. So this increases a lot the costs for Bolivia for exporting and importing goods. One very interesting solution for Bolivia would be to use this waterway that starts in Buenos Aires, in the Foz do Rio da Plata, and then it connects to Paraguay. So El Rio da Plata, that becomes the Paraguay River, that then goes all the way to Cuiabá, and then Cuiabá is a border city with Bolivia. There is already, of course, an existing waterway, but this waterway requires a lot dredging in order to increase the depth of the waterway, in order to increase the capacity that can be transported in this waterway. So recently, so in the last week, people has started projects to dredge this waterway. I think particularly is because of after the huge fires that happened in the Pantanal, they probably had the intention of planting soybeans where there used to be Pantanal, and they probably have a plan to export the soybeans with the waterway. So this waterway is there is a lot of conflict, mainly because the waterway goes through the Pantanal, and the Pantanal is a natural reserve. I mean, whatever is left from Pantanal is a natural reserve, and they don't want to expand into industry and transportation because they are afraid that they will damage the Pantanal. Of course, if we created laws and policies that take care of the environment and is managing, monitoring the environment, and of course you can build this waterway without damaging the environment. But it's very difficult to find common sense in this country, so then they have to destroy the whole Pantanal in order to construct the waterway, and that's what's going to happen, unfortunately. But that's going to benefit Bolivia. We shouldn't just give these benefits to Bolivia to have access to the ocean for free. In my opinion, we should do some business and make them pay for partially, because they have huge benefits for using this waterway. And another waterway that Bolivia would hugely benefit is the Madeira River. So we have 2 dams there. Unfortunately, they weren't built with eclusas, with locks, but the locks can still be built, and if they are built, Bolivia will also have access to the ocean through the Amazon River Basin. So these are other bargaining chips, is that we buy a lot of gas from them, we buy urea, we buy several commodities from Bolivia, and we have a large economic trade with them. We don't care so much about Bolivia, but Brazil should start doing business with the countries around in Latin America. And if we do, we would have access to these huge lithium reserves that we can sell to other countries. So what's happening in Bolivia? So the main reason, so Bolivia has a huge potential, but it doesn't produce. And the main reason is because one reason is because the concentration of lithium is smaller, so it's more expensive to extract lithium in Bolivia, and also the government requires a lot of policies. They require that the lithium is processed in the country, and which investors are not interested. So no one invests in Bolivia. And Bolivia has a very volatile political. It's very vulnerable politically nowadays, right? Because of the coup that happened there. And then you have Elon Musk said that, well, you should take care of yourselves, and if we want to make a coup in your country, we will do. So whatever, just deal with it. He posted a tweet in his Twitter. And then you have Argentina. Argentina also is smaller, the concentration of lithium, but it's smaller than in Chile, but larger than Bolivia. And there is already some production of lithium. So these are the locations where lithium is being produced. Several lithium production locations in Argentina, and this is in Brazil. We have lithium production in Minas Gerais. It's funny that I looked for the mines in Brazil, and it's in English. I didn't find in Portuguese. I found the information in English, which is funny. There are some mines, lithium mines in Brazil. This is the actual picture of the processing plants in order to increase the concentration of lithium oxides. There are different minerals in Brazil. The main one that we extract, which has lithium, the main one that we extract is this one, is ouro-danio, which is a lithium, aluminium, silicium oxide. This is how it looks, stone, nice stone. And I added here all the reference and all the processes, steps in order for the production of lithium. I'm just going to leave it here if you guys are interested. Know how lithium is produced in Brazil. It's very complex, several steps in order to extract and enhance the lithium from the minerals that are extracted. Yeah, so this is the consumption of lithium. This is the production of lithium in Brazil. I already had another graph showing this. These are the chemical reactions required to produce lithium oxides. And this is the last slide, which shows the lithium characteristics, which has gravimetric capacity, gravimetric energy density and volume, and the voltage. So the advantage of lithium is it has a high voltage, but the problem is that it has very few, so there are not many lithium reserves around the world. So of course lithium is very interesting for transportation, but if you want to construct a battery for other means, it might be interesting to look at other molecules, because they have much more abundance around the world. Maybe not for transportation, but it's good to keep your minds open for the other opportunities. People are using lithium-ion batteries for energy storage, for grid energy storage today, which is definitely not the best molecule to do this. Of course, it's cheaper because there's a lot of people investing in lithium-ion batteries. But for grid storage, for example, you can think of several other batteries that would be cheaper. It would be cheaper, of course, if you consider the fact that you have much more resources around the world. Right. Any question, guys? That was the lecture today, talking about the main battery types, and I went through the resources and which countries has which minerals, in, for example, the ocean, deep ocean, where you can extract. So this was the battery lecture. Next lecture, probably I'm going to talk about thermal energy storage solutions. I had to go through a lot of information, so battery has a lot of information. I had to go through really quickly. Didn't go so much into details of each, because it's a huge market also. I thought it was important to broaden your minds of all the possibilities around the subject.